All right, Dr. Hunter, I have a question for you today.
Let's hear it.
Um, what is X-ray diffraction and why is it so important? And why is it in the solid state chapter? Why is it important?
Yeah. Um, well, I can tell you it was important enough to win a Nobel Prize. So that's good. I mean, that's a big deal. Um, so the important thing about it is that these two guys, Bragg Senior and Bragg Junior, they were brothers, or sorry, father and son. Right? Maybe there was a brother too, a black sheep that didn't win the Nobel Prize. I don't know. But, yeah. So what they figured out was that, well, the analogy I have is it's like my son and I in the driveway playing basketball, and you've got two choices. You can shoot for the hoop and put the ball in the hoop directly, or you can make a bank shot. And what the Braggs did was they came up with an amazing bank shot. Basically, here, let me show you on a paper. So the Braggs, which is an awesome name, by the way, because who knows how much trash talking they did, but nonetheless. So basically what they did was they said, hey, somehow we've got these atoms that has some sort of regular shape in them, right? I mean, they probably looked at salt crystals just like you and I look at salt crystals. And the thing that they saw was, hey, those things look very regular, right? And so if they look regular on the macroscopic scale, maybe they're probably regular on the atomic or the molecular level. And so they said, well, imagine if we have a whole load of atoms inside a crystal, but we have no idea how big those atoms are or how far apart those atoms are. And so I assume the Braggs, I have a sneaky suspicion that they might have been German, so they may not have been playing a lot of basketball, but but I don't know that either. But anyway, so what they discovered was a couple of things, or what they figured out was a couple of things, was that if you bounce a wave off of an atom, in this case an X-ray, that's why it's called X-ray diffraction. If you shine an X-ray at a substance, some of it passes through, right? That's how we do X-rays, but some of them bounce off, and some of them are blocked. But anyway, so if you bounce one off and things go well, then you can have you can measure what happens. You can detect this bounced off wave, okay? And conceivably, if you have two waves coming in, they can bounce off. You might get a bounce off two adjacent atoms. And one of the things that we saw when we were talking about nodal planes and atomic structure is that waves sometimes, if they're perfectly in phase, they will constructively interfere. And so you see a bigger wave, right? And if they're not perfectly in phase, then it's harder for they don't constructively interfere. And so if when we shoot two waves at a substance, if the resulting bouncing off waves are perfectly in phase, you can detect these because they're so nicely in phase. So what you basically do in X-ray diffraction is you shoot X-rays at a substance, and the only waves that you see bouncing off are the ones that are perfectly in phase. And so I shoot the X-rays at the substance. What I detect bouncing off must be in phase. And so that tells me something about the particular wavelength that will bounce off. And then through the brilliance of geometry, if we do a little mathematics here, and this is detailed in Cengage, you can work out that the only waves that come off will have a particular wavelength. I got to think about this. I think like this and like this, being in phase with one that comes and bounces off of that one. And because these are in perfect sequence, we can, and because we know how long the wavelength, that X-ray wavelength is, we know how long this distance is between this part of this triangle that I drew and this part of the triangle that I drew. And so we can calculate, if we know this distance, we know this distance, and we know this angle or this angle or this angle, we can then calculate this distance here between these two atoms, which is why we're doing this. We're doing this X-ray diffraction so we can figure out what is the distance between these two atoms that I started off with, and that tells us something about the size of the atom and the positions of the atoms and that sort of thing. So the Braggs took an awesome bank shot, or figured out a technique to take a bank shot, and that if you bank it off the backboard just right, you can detect it going into the basket over here. And based on the angle of that bank shot, there's a little bit of geometry that you can do that will tell you this distance between these two starting atoms. What do you think of that?
Wow, I never really kind of heard it like a bank shot, but now that you mention it, and you drew the hoop at the end, it's visually, I can understand the analogy a bit more, but I think everything you said is great.
Okay, yeah. So the issue is, like a bank shot, this is my backboard, I'm trying to get it in the hoop. Only certain angles of the shot will result in the ball going in the hoop, right? And so it's as if you shoot the X-ray at a different angle because every time you change this angle, you would get a different value of this distance. But this distance is back calculated from when you get the swoosh. Or no, it's not. You don't get a swish. But I mean, you get a bank shot, right? You get the 2 points, right? I guess it could be a 3-pointer, but it's not really it's the knowing the angle that you can detect tells you something about allows you to back calculate this distance. So this is the Cengage diagram. That's obviously neater and tidier than the one that I just drew, but here are the waves coming in. They bounce off the atoms. We don't know, before we do the experiment, we don't know how far apart those atoms are, but by detecting the X-rays as they come off the bank shot, you can begin to figure out what this distance must be. And then the apparatus that they use, they show up here, which is to say, here's the X-ray source. It hits this shield that only allows a very narrow beam of X-rays to come through. It hits the sample. Oh, and here is the detection of those of the diffraction of those X-ray beams. And then some, as you can tell, some serious mathematics goes into calculating back where all the atoms must be. Because when you do the experiment, your sample has trillions, quadrillions, what has a ton of atoms, right? And so you're going to get a lot of different scattering patterns. And so calculating back where the X-rays where the atoms must have been based on the pattern on the photographic film, that's some serious mathematics. But basically it boils down to this Bragg equation that says each one of these waves, if you can detect it on the film, can tell you something about the distance between two atoms. And if you need help actually working through the geometry of those triangles, I can help with that a little bit. But basically it's only the perfect bank shot works for you. What else should we say, Kevin?
I
I think I floored you.
The bank shot was just too amazing. Uh, no, but I think you don't have to be like the Braggs. You don't have to understand what that what the photo, what the result was like in the text. You don't have to understand that. You don't have to be as smart as they are. But if you can understand at least this part and maybe start to understand a little bit of the math and the geometry behind it, you're already learning a lot about X-ray diffraction, and
Yeah.
maybe you'll come to your own analogy, to your own terms as to why X-ray diffraction is important.
Yeah. Yeah. I mean, it basically boils down to it's a technique that allows us to determine the distance between atoms in a crystal. And so that's really amazing, right? I mean, these are unbelievably small distances, right? And we can calculate how precisely what that distance is. And so you can understand that, oh, this nitrogen and this carbon, they're this far apart. Well, except they're not this far apart. They're 10 to the minus 9 meters, right? Right? I mean, I can't press my fingers that close together. Right? They're close, and we can calculate it. Right? So it's pretty sweet, pretty sweet.
Yep, I guess that's all for X-ray diffraction then.
Okay, all right. Thank you, Kevin. Really nice to talk to you. Talk to you next time.
Yep, talk to you next time, Dr. Hunter.